Hi everyone, so welcome to this turbo machines, and now we are in fourth module, that is hydraulic turbines, and now we have come to an end of this particular module by solving this Kaplan turbine. So we will wind up this what we call module. Already we have seen the numerical on Pelton and we have seen the numerical on Francis turbine. So in this video I will teach you how to solve the Kaplan turbine. So we'll move on to the what you call the problem first, the numerical. So the numerical goes like this: a Kaplan turbine under a head of 20 meters develops 11,772 kilowatts shaft power. The outer diameter of the runner is 3.5 meters and the hub diameter is 1.75 meters. The guide blade angle at the extreme edge of the runner is 35 degrees. The hydraulic and overall efficiency of the turbine are 88% and 84% respectively. If the velocity of the whirl is 0 at outlet, find a runner vane angles at inlet and outlet at the extreme edge of the runner. Next one, we have to find out the speed of the turbine. So this is the problem given. So first let us see what are the data given. So head is given for the Kaplan turbine. So clearly it is mentioned in the problem that it comes under Kaplan. So Kaplan turbine head of 20 meters. So H is equal to 20 meters, develops 11,772 kilowatts shaft power. So that is the power given. The outer diameter of the runner, see capital D, is given as 3.5 meters and hub diameter is 1.75 meters. So this we can take in as small d or db, that is a boss diameter or hub diameter, right? And the guide blade angle at the extreme edge of the runner is 35 degrees. Okay, so blade angle is given, so that is beta 1 is given, and then the hydraulic and overall efficiency, the guide blade angle at the extreme, so that is alpha 1, that is 35 degrees. Because why it is taken as alpha 1 is because here it is given as guide blade in the sense it is acting as a nozzle, because guide blade is also called as a fixed blade or nozzle. So always nozzle angle will be alpha 1. So that is what it is given. Guide blade angle means it is alpha 1. Alpha 1 is equal to 35 degrees. So next one is the hydraulic and overall efficiency of the turbine are. So hydraulic efficiency eta naught is equal to 88%. Eta H is equal to 88%, and overall efficiency eta naught is equal to 84% respectively. So if the velocity of whirl is 0, that is Vw1 is equal to 0, Vw2, because if the velocity of whirl is 0 at outlet, that means Vw2 is equal to 0. That's what it is said. So they are indirectly saying that if Vw2 is equal to 0, then it will become a right angle triangle. Okay, so that is what we need to understand first. So the runner vane angles at inlet and outlet at the extreme edge of the runner. Okay, so we need to find out the blade angle or vane angle, that is beta 1 and beta 2 we need to find out, and then the speed of the turbine. So we need to find out the capital N. So this is what, so it also looks simple, so nothing complication is required, is available over there. So we need to find out. So what is the data? Once again, head is H is equal to 20 meters and shaft power developed, that is P is equal to 11,772 into 10 cube watts, and outer diameter, that is d0, is equal to 3.5 meters, and hub or boss diameter, that is db, is equal to 1.75 meters, and guide or fixed blade angle alpha 1 is equal to 35 degrees, and hydraulic efficiency is 88%, that is 0.88. Overall efficiency, that eta naught is equal to 0.84, and whirl velocity at outlet, that is Vw2 is equal to 0. Then outlet triangle, that is right angle triangle. Now we need to find out the runner vane angles, that is beta 1 and outlet is beta 2. So the inlet velocity triangle is drawn after knowing the V1. So obviously for inner triangle nothing is given, that we have to draw this particular only, but based on the Vw1 and you need to compare both, and based on that we need to draw the inlet triangle. And but exit triangle is always right angle, because it is given that Vw2 is equal to 0. So that's what it is given in the problem. So we can understand that exit triangle is right angle triangle. Now, so we need to find out that flow velocity. So here we need to find out so Q, the discharge here. Okay, first what we need to find out is we need to find out beta 1 and beta 2. Okay, so before finding out this beta 1 and beta 2, so we will try to find out VW1. So then U1. So if you know VW1 and U1, we can understand and analyze so what kind of triangle we need to draw first. So for that, so flow velocity Vf1 is equal to Vw1 tan alpha. So in this, with respect to that, yes, so from here, so first and foremost, we need to find out the flow velocity, that is Vw1 and tan alpha 1. So from here we can get the value of Vw1, but we do not know what is alpha 1 is given the problem, so no problem, but Vf1 we do not know. So for that, so two unknowns are there, that is Vf1, Vw1. So we need to find out how to find out this Vf1. So where do we come across this Vf1? So we have another formula like discharge formula, Q is equal to pi by 4 d naught square minus dB square into Vf1. So from this we can find out the flow velocity. Anyways, outer diameter is given and boss diameter is given. So, and discharge, but we do not know the discharge again. So we need to check where the discharge is available in some other formula. So again, the overall efficiency is given in the problem. So overall efficiency formula is equal to PS divided by rho g QH. So in that, power is known, overall efficiency is known, and rho density is constant value, G is constant value, H is given. So only unknown is Q. So here we can find out Q value. So with this, Q is equal to PS divided by eta naught into rho into GH. That is equal to 11772 into 10 cube. We need to put in watts, divided by overall efficiency is given as 84% and density is 1000 and G is equal to 9.81 and H is equal to 20. So with this, so we will get 71.42 meter cube per seconds. So this is the discharge value, and we can substitute this discharge value in the equation number 2, that is Q is equal to pi by 4 d naught square minus dB square into Vf1. So if you substitute all the values like discharge 71.42, pi by 4 into 3.5 d naught, and dB is equal to 1.75 squares and Vf1. So unknown is Vf1, so Vf1 is equal to 9.9 meters per second. The same Vf1 value substitute in the equation number 1 again, which is Vf1 is equal to Vw1 tan alpha 1. So in this Vw1 we will get it. So Vw1 is equal to 14.13 meters per second. So finally we got the value as Vw1. So we need, again we should know what is U value. So how to get this U value? Get the hydraulic efficiency formula. So eta H is equal to U1 Vw1 into G into H. Hydraulic efficiency is given as 88%. Vw1 just now we have found out. G is the constant value. H is given in the problem. So the only unknown is U1. That is U1 is equal to U is equal to 12.22 meters per second. So we need to compare both Vw1 14 and U is equal to 12.22. So which is greater? That Vw1 is greater and U is smaller. So with this we understand that it is a normal triangle. So we can draw the inlet triangle immediately. That is a normal triangle. Okay. So we draw the inlet triangle, that is U1 is smaller. Make sure that U1 is smaller and Vw1 is greater. Okay. And then, so we need to find out now beta 1 we need to find out. So exit triangle, as usual, we can draw the right angle triangle. Okay, so which is alpha 2 is equal to 90 degrees and Vw2 is equal to 0. So with that we can, both the triangles we can write. So now our intention, the aim is to find out beta 1 and beta 2. So from delta O1 BC, from the triangle, tan beta 1 is equal to Vf1 by Vw1 minus U1. So with this, beta 1 is equal to 79 degrees. The same way, tan beta 2, that is equal to Vf2 by U2. So beta 2 is equal to tan inverse of 9.9 divided by 12.22, that is 39 degrees. Next, to find a turbine speed, that is speed n. So where do we come across this speed? U is equal to pi dn by 60, where d we have to take outer diameter d naught. So from this formula, n is equal to U into 60 divided by pi into d naught. So you will get n is equal to 66.68 rpm. So this is how we'll find out the speed, and just will go through one of the things that it is beta 1 beta 2 we need to find out, and all the other things are given. But for drawing the triangle, VW1 is missing. VW1 formula, three different formula we used. One is VF1 is equal to VW1 tan alpha 1. Discharge Q is equal to pi by 4 T naught square minus dB square into VF1. Overall efficiency eta naught is equal to PS by rho QGH. These three formulae we used to get this VW1. And then for U1 hydraulic efficiency U1 into VW1 to G into H. With this U1 also we found out, and then we decided this is the inlet triangle and that is exit triangle. So from this tan beta 1, using the tan beta 1, so we found out beta 1 angle. We using tan beta 2, we found this beta 2 angle. And for speed, U is equal to pi dn by 60. With this n also, the speed also we found out. So this is how we will find what we call solve the numerical on Kaplan turbine. So thank you for so much for watching this video. Thank you.